Okay, everyone, thanks so much for your patience and for coming and for joining us for the second in a series of lectures celebrating the 20th anniversary of the MRI Coordination Office here in Bern, Switzerland. My name is Gabrielle. I'm a scientific project officer at the office, and we're joined also by our executive director, Carolina. I hope she'll be able to perhaps introduce herself and say a few words later when we get the camera issue resolved. But in the meantime, we're very happy to have Maaike Bader joining us today from the University of Marburg to, like the Lorax, speak for the trees and tell us about the stories that Alpine tree lines can tell, interpreting spatial patterns of treeline ecotones. And as with our other MRI Anniversary Lectures, we'll have approximately a 40-minute presentation from Maaike, followed by 10 to 20 minutes of Q&A. So we hope you'll be very active and engaged using both the chat features and the Q&A feature, which, if you have it, looks like two chat bubbles at the bottom of Zoom. You can use it to ask questions and also upvote questions if you have the same questions that others share. So thanks again for joining us. Maaike, perhaps you'd like to introduce yourself and get going with the talk. Thanks again, everybody.
Okay, thank you very much, Gabrielle. Yes, I can very shortly introduce myself. My name is Maaike Bader. I'm from Holland, working in Germany at the University of Marburg as a professor of biogeography. Yes, and I did my PhD on Alpine tree lines, and it's still my favorite topic ever since. So I'm very happy to be invited to talk about that topic here today. So now we should be moving to the next slide, and we are not. Why are we not? I'll try something else. No. Try something else again. Sorry. Advance to the next slide. Yes. Yes. Okay, it works. Yes. So this is a random demonstration of why this is my favorite topic in the world, and also my favorite place in the world. It has two advantages as a favorite place, because tree lines occur all over the world. So there are a lot of places in the world that are favorite. And as you probably appreciate, oops, sorry, now it goes too fast. As you probably appreciate from this picture, it is also a very beautiful part of the mountains. We have there two very important ecosystems, the mountain forest and the Alpine zone, that come together, both having their unique biodiversity, their unique biophysical properties. So it's a very, for us as humans, I think it's a very attractive feature in the landscape, but also ecologically, it's a very important boundary. It's important in itself, and it's also important just as the delimitation of two very important mountain ecosystems. Of course, tree lines have drawn attention of researchers for a very long time, and it has also been observed already a very long time ago that tree lines occur all over the world, and there are certain patterns that we can observe in tree line elevation if we look at different parts of the world. I think you can see my mouse, which I will use as a pointer. So this is a drawing by Alexander von Humboldt, where he observed certain geographical patterns. One of those is that in the Andes, this is the tropical Andes here, the tree line is at quite high elevation. At the subtropical island of Tenerife, it's at a somewhat lower elevation, but at subtropical continental mountains, it's again at a very high elevation. In fact, at the highest elevation that we have. And then, of course, when we move further towards the pole, the tree line lowers in elevation until it reaches sea level at some point. And we are more at the Arctic than at the Alpine tree line. These observations have been elaborated upon more, and it is in fact possible to model the elevation of the tree line just by looking at temperature or at growing season length and temperature conditions. And so this is a picture from a very famous paper by Paulson and Kerner, where the tree line elevation was modeled at a global scale based on temperature, and the best fitting model was the one where the growing season is more than 94 days. That's one criterion, and the mean temperature of that growing season should be about over 6.4 degrees. So the tree line is more or less located at a mean temperature, a mean growing season temperature of 6.4 degrees, which is quite astonishing, because I think as ecologists we all realize that an average temperature actually does not have much meaning for an organism. And all the same, this average temperature has the best explanatory power for tree line elevation. If we look at this figure, there's several other things that we can see that are quite interesting. So the green line is the equator. And we see that the equator is not in the middle of this shape. Right? So we see that in the northern hemisphere, elevations, tree line elevations are a little bit higher at the same latitude as the southern hemisphere, which does not have to do with different conditions, or it does have to do. It does not have to do with differences in the tree physiology or the properties of the trees, but it has to do with the bigger landmass on the northern hemisphere leading to higher temperatures at the same latitude. And that's also this variation that you see here. It's actually the upper ones are the upper tree lines are those where the conditions are more continental, so it's actually warmer at a higher elevation than it is in more oceanic situations. So we have an astonishingly good fit of the model, so of the measured temperature, the measured tree line elevation and the predicted tree line elevation. So if we consider that temperature has such a strong correlation with tree line elevation, then of course this makes us wonder, if the temperature increases, which it is currently doing, then what's going to happen to the tree line? Now the next slide is going to be important, because we're going to talk about what the tree line actually is. So the tree line, in the sense of the potential elevation where trees can still grow, that is going to increase with increasing temperatures. There's no discussion about that. In fact, because if the temperature is the determinant of that tree line, and of course if that temperature is going to be somewhere else, then the tree line, in the sense of potential tree line, is going to move. Whether the actual transition between forest and non-forest, so the tree line ecotone, whether that is going to move upwards as well, that is a very different question. So this was a slide I said was important. It's defining what are we actually talking about here. What is a tree line? So one question, is it a line? This of course depends on the scale. If you look at it from far enough above, yes, then you can define it as a line. If you zoom in, then it starts becoming a transition zone. And the transition zone can be defined as the zone between the timber line, whatever that is, or the forest line. I like forest line better, where there's still closed forest, whereby closed forest is also regionally different. Between that line and the tree species line, so the line or the elevation at which the last individuals of tree species still occur. They don't need to be tree shaped at that elevation. They can be cromholes, so stunted individuals, or they can be even the seedlings. But that's that whole zone between the upper, so between the closed forest and the uppermost individuals of trees, tree species, that whole zone is the tree line ecotone. And that is what I will be talking about today. And this is something else than the potential tree line. The potential tree line is where the trees could grow. The tree line ecotone is the zone where trees actually stop growing at this moment. And there are several possibilities why those two might not coincide. One is because the climate might have changed and the trees are not keeping up. So the tree line ecotone has not moved to the elevation where it could be theoretically. Or it could be because of disturbances, be it human disturbances or natural disturbances. The trees might have been removed in the area where they could have grown, or where they might even have grown in the past. So that's important. So we're not talking about potential tree line here today. We are talking about the tree line ecotone. And this tree line ecotone can have very different shapes in very different parts of the world. And I think, or we think, that that is an important feature, that we can learn something from that. And that's why the title of this talk was, what what treeline can tell us. So I'm not going to talk about all the historical events that treelines might have lived through because they are so old or anything like that. That is also very interesting, but I'm going to talk about what they can tell us by the patterns that they show us. So this is a tree line on Sajama, that's a volcano on the Altiplano in Bolivia. And there is like a strip of forest, of very open forest, polylepis forest around that volcano, which thins out gradually as you go upwards. And at some point, they are just sort of little shrubs. Okay. That type of spreading out of trees getting spread out and getting smaller also can be found, for example, in the Alps. In the Alps, you really have to look for it. There are not a lot of places where such a pattern can be found, which is probably due to human land use. So this is probably quite a natural pattern, what a tree line would look like if it would be undisturbed. And in the Alps and in European mountains in general, that is not very often found anymore. This is in the Pyrenees, where you have a similar pattern. I'm not saying that this is a natural tree line necessarily, so there's a lot of grazing going on above the tree line. This area here is full of sheep, but you can see that the tree line does have this pattern where the trees are getting smaller and they're spreading out, and then at some point there are none left. This is a very different situation. This is in New Zealand, and this is it's not Nothofagus anymore, but it's a what is it? I actually still put Nothofagus menziesii. I think it's now Lophozonia, or I can't remember which one. So these Notophaguses in New Zealand have all been renamed, but they are still in the Nothophagaceae, in the family of Nothophagaceae. Sorry, I'm speaking German now. Anyway, you know the family I'm talking about. So, and these trees, so the trees in this family, tend to form very closed, abrupt tree lines like this, where you do not have this transition zone of trees getting slowly smaller, or they do get a little bit smaller, but they don't spread out. They reach the tree line in a closed front. And that's a very different tree line than the ones that I've shown before. So this in the background here, and in the foreground, you also see the tree line here. Another thing I wanted to show with this picture is another level of patterns that tree lines can show, which I will not be talking about today, but which is important to also keep in mind. So I will be really talking about the structure of this transition zone. So is it gradually getting more open and shorter, like I showed before, or is it abrupt like this? That's what I will be talking about. Other patterns that are also interesting and that can also teach us something about what happens at a tree line are these landscape patterns. Oops, that's too fast. So, and you can see that here, for example. So you have this tree line is actually all at one elevation, right? But then you have these dips in the tree line. And in this case, so partly that is just rock slides going down there, and also avalanches that may come down, for example. And in other parts of the world, you might have different patterns. So in many tropical mountains where avalanches are not really important or ever occurring, there you might have that the forest actually goes up higher in the valleys than it does on the ridges. So you can have very different patterns that also tell us something about processes, but that's a different level of processes, mostly disturbance processes that I will not be talking about today. This is another tree line also in New Zealand, but on the other side of the Southern Alps, where it's much wetter, and we don't have Nothofagus there anymore. And so the forest we have there is a mixture of podocarp, so podocarp species and broadleaf evergreen species, and they transition into the Alpine zone very differently again. So this is still the forest, obviously, and here, somewhere here, there's the transition between this forest. And here, the yellow part, the yellow smooth-looking part is the Alpine zone, which is like this, is like tussock land, and in between there is a transition. But it's not really an opening up of the forest so much, but it's more trees getting smaller and trees changing species. So there are different species forming this transition zone than the forest here below. So again, it's a very different situation. And this is a very funny tree line from the Rocky Mountains, where you have these tree islands. So you can't, so the tree line is somewhere up there, or it would be up there if the mountain were a little bit higher, but it's this very interesting situation with trees clustering together. Okay, so having looked at some examples here, and of course there are many more, what we've been trying to do is to try to find some order in this, to try to not so much classify them. So classification always has the danger of drawing lines between black and white or whatever. And of course, the tree lines are not black and white. There's all sorts of tree lines with a lot of transitional forms in between. But still, in terms of talking about these tree lines, I still think it is useful to use certain terms for the extremes of these of this gradient. So for example, here I would say this is a gradual tree line, and here I would say this is an abrupt tree line. And then of course some tree lines are somewhere in between, and it's really hard to say, is it really gradual or is it already abrupt? But apart from talking about the details of which tree line is what, I think it's still useful to try to use some terminology there. And another reason to describe them, so one is naming them, but the background behind that, of course, is describing them in different dimensions, which helps to try to then relate these dimensions or these patterns to the underlying processes. I already mentioned improving communication, that's just hanging names on things. And I think it is important to recognize that some tree lines are more similar than others, so that these recurrent tree lines can be used to extrapolate research findings. So if we do research at a very abrupt tree line and we have and we find that, I don't know, for example, the dynamics of this tree line is very slow and it depends on very strongly on seedling establishment or something like that, then it is more likely that another abrupt tree line has a similar situation than a tree line that is gradual, like this one at the top, for example. So that is another reason to try to get some order in all these patterns. And these are just some pictures. I will talk about these patterns later, but this is just two directions how you can look at a tree line. One is looking at it from the side, of course, what happens to the trees as you move up the mountain, and the other one is looking at it from the top, and how does the transition from the forest, so the green of course is the forest and the brown is sort of alpine zone, what does this transition look like if you look at it from above? And why is this important? Well, these recurrent patterns and the extrapolations we might do between them, that does not just come out of my head. It is actually also based on some observations. And one of the observations is that looking at diffuse tree lines, so this is a graph based on a literature review by Melanie Harsh. And the literature reviews she did revealed that diffuse tree lines tend to have advanced or have shown increased advance in recent years. Whereas Krumholtz tree lines, for example, so tree lines that are characterized by, so this one at the bottom, so trees getting really stunted towards the top. So Krumholtz tree lines tend to not have advanced very much. So tree lines with different patterns, and also, of course, the abrupt and the island tree lines had very few observations. So it's very hard to say something about that. But if you would take these graphs just by, just visually, you would also suspect that the abrupt and the island ones also tend to not advance rather than advance. So it's quite a big difference between these tree line types. And this is quite an old paper, like 10 years ago, but a newer paper by Amanda Hansen also showed, where she did another literature review, like updating this information, and she used 3 categories for tree line types, and she also found that the diffuse type showed more advanced than no advanced. In this case, the advance was defined by really an upward shift, so it was nothing to do with infilling or other types of change that you can see in a tree line ecotone, but really an upward shift of the tree line itself. So there seems to be some relationship between these patterns and dynamics. So that is something that not just me, but also quite a lot of colleagues are interested in. And thanks to the MRI, we could do a synthesis workshop already in 2017 in Jaca in Spain, where we talked about these topics, and we sort of developed a strategy of how to study these pattern process relationships. And this year, finally, a paper based on this workshop and all the discussions was published in ecography, and a lot of what I talk about today is actually also in that paper, if you're interested in the details. So one of the consequences of this MRI workshop was another series of workshops that were funded by SDIF, the Synthesis Center of IDIF, which we called S treelines. So they had to have a name with S at the beginning. So they are called S treelines. And here again, we were looking at the spatial patterns, and here the focus was on modeling these processes. So developing the methods and modeling them, and also talking about global data collection. So how can we bring together data that help us to understand these patterns better? So the research questions for these workshops were, so what are the processes that control treeline spatial patterning and dynamics? That's sort of the important big questions. Related to that, how do these spatial patterns relate to dynamics, in particular, of course, in response to climate change? What causes regional differences in these patterns and also in the elevation of the tree line? So these are related to each other as well, of course, the pattern and the elevation. And of course, how will different tree lines respond to climatic changes? So looking at global patterns in the patterns and global patterns in the dynamics. And now I'm going to present a bit of a conceptual model that is sort of the basis for what we are talking about. It's quite simple, really. So what we're trying to explain is the tree line form here at the top. And what we are using at the moment in our model is trying to use the simplest possible explanation for this. And the simplest explanation is that the tree line is formed due to a combination of three main processes. One is growth limitation, so how fast do the trees grow, or can they grow at all? Another is dieback, so biomass being lost, usually because of different stresses. And another one is mortality. And a lot of the mortality will be seedling mortality, but of course, sometimes you also have adult trees that can die. And these three processes we are calling first level mechanisms. So they are really the basic things that happen that form a tree line. Of course, they don't happen just like that. These processes are influenced by different second level mechanisms. And one of them is growth limitation. Growth limitation is mainly related to a lack of warmth. So if there's not enough warmth for growth, and warmth being temperatures above about 5 degrees, so if there's not enough of that, then the trees won't grow. This is a count of leaf scars to estimate the size of the age of this tree. So this tree, which a lot of people would refer to as a seedling, was actually, I think we were about 30 years. So this is a 30-year-old tree growing in a very exposed and very cool environment in the Rocky Mountains. So here growth limitation is obviously a problem. Other second level mechanisms, maybe frost damage, for example, here in Nothofagus, or previously Nothofagus in New Zealand, and that is not able to grow out of its cage. Snow mold can be a problem, winter desiccation can be a problem. These are all different, so these are more like winter damages, these are more like spring and autumn damages. This is more a growing season problem. So this all of these mechanisms might cause, for example, dieback. No? So winter desiccation, snow molds, they cause, and also frost damage, they cause dieback. They might also cause mortality. Of course, these second level mechanisms are dependent on climatic conditions. And the climatic conditions in turn are determined by not just the general macroclimate, but also by the local conditions. And part of those conditions can be things like rocks and small topographical differences, but also the vegetation itself. And that is quite important for this whole concept, that there is actually a feedback. So the tree line form causes a modification of the climate. For example, by a redistribution of the snow. So for example, these strips of trees, they They cause snow to accumulate on one side and to be blown out on the other side. Also, of course, shading is a very important effect of vegetation, and also wind redistribution. So it's inside this, this is a little tree island here. Inside the island, of course, the wind speeds are much lower, but around the island, the wind speed may actually be increased because they are redistributed there. So this we refer to as third level mechanisms. They are more the vegetation feedback mechanisms. So these first level mechanisms, why are we distinguishing these two things? Well, one is because first level mechanisms may be the same and lead to the same pattern, even if the second level mechanism is different. So this is an example, again, Notofagus treeline in New Zealand, where from this experiment, so this is an experiment by Peter Wardle that was started already in the 70s. And this photo, I took this photo, I don't know, 2010 or something like that. So this is 30 years after the experiment was installed. And here you can hardly see it. There's a Notofagus tree that was planted in this shade cage, and it survived there. It didn't die, but it never managed to grow out of the cage. Whereas other tree species that were also planted in the same area, they grew into big trees. They had like big stems, and they were several meters high. So this Notofagus species is not able to grow out of the cage, and the reason is probably because it gets damaged by a combination of too much solar radiation and too much night frost. At least that's what it looks like. So this is a mechanism that growing outside of the forest here is not, also establishing outside of the forest is really difficult for these trees. So the mortality, the seedling mortality outside of the forest is very high. I will explain this graph as well because there will be more of this graph, so it's important. Oh, I'm just going to close my window because there's, I don't know, building outside. Sorry, I hope it's a little bit quieter now. Yes, so this graph is quite important. Hang on, I've lost my mouse. Here it is. Okay. So these graphs, there will be more of these graphs. So this is supposed to be just the ground, and these are trees. These green arrows are trees, and these three lines, they represent these three first level processes. And in this case, so this dotted line is the growth limitation. Growth limitation is always a point at tree line, but in this particular case, growth limitation doesn't really affect the tree line very much because there is something else happening before growth limitation gets really bad. And in this case, it is this mortality. This mortality is suddenly rising at the edge of the forest, which is because of a positive feedback. So inside the forest, mortality is, of course, there will be mortality, right? There's always mortality in seedlings, but inside the forest, mortality is relatively low and the seedlings are happy, and outside they cannot establish because of different stresses, in this case, maybe frost and radiation stress. And in this case, I put dieback at 0 because for this type of tree line, we don't really need dieback. So in these graphs, if one of the processes is just at 0, it doesn't mean that it doesn't happen, but it means that it's not necessary to cause this pattern, right? So this is the minimal, like sort of a minimal model, like only the processes that are really necessary are drawn, except from growth limitation, because that's just always happening. So that always basically looks the same. Okay, so this is one example of an abrupt discrete tree line. This is another example of an abrupt discrete tree line. This is a tropical tree line in the north of Ecuador. Here you can see the picture. It's also very abrupt. And in this case, the first level mechanisms are the same. There is high mortality outside of the forest. The second level mechanism is partly the same, actually. So there is actually also radiation stress limiting a lot of the species from this forest. But the point I'm trying to make here is that a totally different second level mechanisms, which is fire, also maintains this abrupt tree line. And in this case, it's just because the forest, this is a cloud forest, so it's very mossy and almost always really moist inside. So the microclimate is very different and quite moist inside this forest. Whereas here in the Paramo, also outside of the forest, the grasses can get really dry when the sun comes out, and then they burn really well. So if there's a fire, it usually would stop at the tree line. So any tree seedlings that we're trying to establish here would disappear, whereas the ones inside the forest are fine. So you have the same type of situation. There's high mortality outside the forest, low mortality inside the forest, even though the second level mechanism is quite different. So I'm not expecting you to to understand this figure in one go. I explained the general principle with these 3 lines, and I will go through some of these examples. So this figure is in this paper. So if you are interested, you can look at it there. I will now just go through a few examples to explain a bit more what we're trying to do there. So the one in the top left corner was a gradual discrete tree line. Maybe to the terminology. So gradual refers to the size of the trees slowly getting smaller. The opposite of gradual would be abrupt. Discrete refers to the end of the forest being a closed front. And that is, and the opposite of that is diffuse. Okay, so the gradual discrete tree line is a situation where growth limitation is actually the only thing happening. So trees are getting more and more restricted in their growth, so they stay smaller and smaller until at some point they can't grow at all. So for this tree line, we don't need dieback, we don't need increased mortality with elevation. So in my mind, this should be the null model. If the tree line is really only determined by growth limitation, then the tree should only get smaller. They should not get fewer. This is a picture from Ecuador, from the south of Ecuador, where you also have quite a smooth transition from here from the forest to somewhere there. There's the Paramo. Right, so here at the right-hand side, you can always see these 3 first level mechanisms, and the one that is important is circled, so it's growth limitation in this case. Now I already said the opposite of discrete is diffuse, and the diffuse tree line, in a diffuse tree line, there's still growth limitation going on, but there's also mortality going on. But here in this case, I drew the mortality as a sort of sinus line, because if you have a smooth increase in mortality, then if you model this and you leave it run long enough, then at some point the whole area will grow, will be closed. So it is possible to get a diffuse tree line in a model, but then you need to have quite a close balance between the age of the trees and the chances of establishing. So they have to establish more or less at the same rate as that they die, so that they don't all disappear, but they also don't all start filling in the space. And I don't think that is actually what is happening. I think that to get a diffuse tree line, what you actually need is some, be it spatial or temporal variability. So you either need microsites that are more or less suitable for tree growth, and then the ones that are more suitable might grow a tree at some point, and some of them never will. Or you might have temporal variability, where in some years you have trees establishing, and those that establish stay there, whereas then there will be a lot of years when no trees are able to establish, and then you're more likely to get a diffuse tree line like this. So here there's already a second process being important. Next to the growth limitation, it's also mortality. Then we already saw the abrupt discrete tree line, for example of New Zealand again. I wanted to show here again, just to show this little figure here, because what is interesting about these tree lines is that they very likely have quite a strong hysteresis. That means if you come, so in this zone, there is quite a large area that can be either alpine or forest, depending on where you come from. So that is shown in this graph here. So the vegetation type is on the y-axis, and at the top you have forest, and at the bottom you have alpine vegetation. If you have forest, then whatever it is, the stress factor or the resource is at a certain high level. So let's say it's no. Sorry, I'm not. This was not correct. So if you're in the forest, then there is some zone, like this first zone, where you always can form a forest, where there will always be forest because the conditions are just really good enough for trees. Then there is a zone where if you have trees, the conditions are good enough for more trees to establish, and the forest can maintain itself. But if in this zone, and if in this gray zone, if there aren't any trees, then the conditions are such that trees have a really hard time to establish. So if you come from this side, so if there is a disturbance and the trees are removed, then it can take a really long time for trees to reestablish. Whereas if the trees are already there, they can stay there. That also means that if the climate gets worse, the forest might still maintain itself. Whereas if the climate gets better, it is very hard for the forest to move. So these tree lines tend to be really stable. It's very hard to move them when the climate changes. Right, so here's just some other examples. So another aspect that we are looking at is at the deformation of the trees. So the formation of Krummholz. Krummholz is a nice German word for crooked wood. So basically just means stunted and deformed trees. And of course, for Krummholz trees, you need this dieback gradient to be stronger. So at some elevation, and usually this is related also to, for example, wind exposed slopes, then the trees get damaged regularly and they cannot grow into a tree, even though they might be able to grow quite okay. Of course, if they are able to grow too well, then they will grow out of the stressful zone quickly, and then they might be okay. So it is still a combination of growth limitation and dieback, but the dieback is actually the strongest. So this is an example from the Pyrenees, where you have this Pinus uncinata, which is normally a tree. And in this case, it's quite a windy site, and this bush here is not able to grow into a tree because it's dying back. And it's not because it cannot grow so much. Actually, being a bush like this, it probably can grow better than if it were a tree, because it can maintain its warmth better than it could if it were a tree. Then I already showed this one. You have these island situations, and the island, I sort of like tree lines with islands because they have interesting feedback processes going on as well. Because inside these islands, you can see that's particularly here where you have this windy situation where you have trees establishing in the lee of each other, but also here where you have trees. So these might either be clonal, of course, these groups of trees, but they also provide shade for seedlings to grow. So they might not be these might not be single clones, but there may be combinations of different individuals as well. And that is found at quite a lot of tree lines as well. So there we have, so for the island pattern, the important point is mortality. So mortality in between the islands. But for the Krummholz islands, of course, their dieback is also very important. Okay, so that was a lot of talking about a lot of examples, and that's all theory. And what we, of course, are interested in is now getting into more detail, like really studying and trying to, I wouldn't say prove, I don't like the word prove, but let's say prove a point and see whether the processes that we hypothesize are really happening, and what is happening in more detail. So to work on that as one of the outputs of the MRI and then the treelines workshops, we are now developing a model which we call the STEM model, the spatial treeline ecotone model. And this is an individual based model, which means that each tree is modeled individually, and it has explicit spatial neighborhoods of other individual trees with their own sizes. And it's pattern oriented. That means that we are trying to reproduce different types of patterns, the spatial patterns, of course, I've talked about it a lot, but also if we have data on temporal patterns, we also, of course, try to reproduce those. And it's also things like size distribution, population structure, etc. And the more of those patterns fit our model, the more we believe that our model is making sense. So the first thing we are doing now is modeling these first level mechanisms, and the second step will be to also model the second level mechanisms, so to get more into climatic gradients and microclimatic effects. So this is the current status. To the left and right, you see some example of the model world. We are using NetLogo for this, which is a dedicated individual-based modeling platform, which is actually quite easy to learn. So it's nice because others than the model developers can actually understand what's going on. And these are just two examples of the type of output we have. So this is a gradient from low on the mountain to high on the mountain, and trees are getting, in this case, they are mainly getting smaller. The different tree sizes are different tires. So we are modeling the trees so the seedlings have different model parameters than small trees that are still in the protected zone, but not seedlings anymore. And then trees grow out of that protected zone into adult trees. So they are different, different groups of trees. Yes, I think I need to speed up a little bit, otherwise we don't have time for the questions. So yes, so now at the moment we're just doing these first level mechanisms, and we are basically trying to verify that, or trying to reproduce our conceptual models. So everything I've shown so far, we're trying to produce that with a formal model. And the formal model helps us a lot to realize that certain logic that we are following in our head actually don't work maybe so well. We need maybe some extra elements to be able to really produce the patterns that we think we should be producing. To make sure that we have more or less realistic patterns, we are first, at this stage, we're just seeing that the model is producing a forest that really is possible with tree sizes and tree densities that is possible. And then we will compare this model output to actual field data. And this is our dream field data. This is data from Julio Camarero from the Pyrenees, where he actually mapped this and noted the size and the age of all the trees in quite big transects up the tree line. And of course, that is perfect because that is exactly what we are trying to model. And then we're using these different dimensions to decide whether our model really fits the data or not. We are looking at these different dimensions. So we're looking at how abrupt is the height change of the trees, how much deformation is happening in these trees. So these are the stature changes. We're looking at it from the side, and then the patterns in the XY plane is what you would look at, what you would see from above using, for example, aerial images. And then we're looking at, so do we have a discrete boundary, or do we have this this diffuse change, or do we have a clumping of the trees into islands? Those are all criteria to evaluate this data. And of course, now what we need to compare the model against is real patterns. And we don't have so much of this dream data like we have from the Pyrenees, but what we can do is use remote sensing. And that's something we're also developing at the moment, like how to efficiently use remote sensing to describe treeline spatial patterns. In the ideal case, of course, we have aerial photos and LiDAR images, and then you can really do a 3D mapping of the trees. In a lot of cases, we might only have aerial images, and then we can't do 3D imaging, but we can do 2D imaging at least. So the nice thing about pattern-oriented modeling is that you don't need all the patterns all the time. Of course, the more patterns you have, the better. But if you have something like this, so this is just seedling distribution inside the forest to the left, and then outside the forest, some species are more and then getting less. This as an example of the type of data that you can also use to evaluate your model with, even if it's only part of the patterns that the model could be producing. And this is my my second but last slide. So to collect this type of data and to try to collaborate with different researchers to get an overview of what type of tree lines we have in different parts of the world, one of the things we've done is created this web GIS where we have started putting in tree line points. So this is a point in Ecuador, actually. So when you go on this point in Ecuador, you get a pop-up and then you get a picture and you get some general information like the elevation and where it is. And for example, the tree species and the shrub species. So this is the state that we have it at the moment, where you have some basic information. You can see that the distribution of the points is still quite limited and not very balanced. So if any of you has tree line points that they want to contribute, please contact me. We would be very interested in including those, and also including any other geospatial tree line information. We can add new layers also to this project. And this map is part of a website that is also trying to bring together information about tree line and tree line patterns and resources that we have, and then the network that I showed. So if you are interested in all that, then please go to the website. And there's even a mailing list, although I must admit I never sent any emails to it, but at least it's good to have, you know, to have an overview of who's interested, and if there's something important, then I would actually send an email about it. Okay, so that would be my last slide, thanking everybody. So this, I think it's probably clear that what I talked about is not just my idea, but it's based on a lot of discussions with a lot of tree line researchers. So I would like to thank everybody, and also, of course, thank MRI for initiating this this nice group of people as a team, and SDIF for also funding our Tree Lines workshops, and the DFG for also co-funding some of these activities. And of course, you for your attention.
Thank you so much, Maaike. We want to make sure everybody has the opportunity to ask questions. So again, the ways to do that are all found along the bottom of Zoom in the bar. So you can use the chat to type a question. You can raise your hand if you would like to have us unmute you, and you can ask your question using audio. Or you can use the Q&A feature, and I see someone, I think, wished you good morning, Maaike, in the Q&A just now, but you can use the Q&A to open questions, upvote questions. So you definitely have some options. I'm sure I have a few, and my colleagues from the MRI office who are also here might have some as well, but we want to open it up to the audience first. And thanks again. I think we're all spending so much time looking at screens. It's a nice change to look at a screen and see at least pictures of trees and these wonderful landscapes where you get to do your research. And while we're waiting for everyone to come forward with questions, I also want to quickly share. Oh, sorry, question from Walter in the chat. Maaike, would you like me to read it, or would you like to read it? I think you're on mute.
I would. So what's the website? So the website is alpine-treelines.net or the .org, or we have several domains, but the .net, and then you are forwarded to the .de one actually. So it's alpine-treelines. Whatever, net, de, org, or com, I think.
Okay,
yeah.
And then it looks like there's another question in the chat as well.
Thank you for the Yeah, that's a very interesting one, the root growth. So the question is whether, to what extent root and soil growth, soil temperature cause diffuse tree lines. So I know that in boreal forests, where you have permafrost, there it really can happen that if one tree grows, it shades its own roots, and then the permafrost doesn't melt, and there's a, like, it really directly influences, like it prevents the forest from closing. I personally cannot, but I would really be interested if you have an idea. So I cannot imagine a mechanism. So this would only kick in when the tree is already there. When the tree starts growing, then it starts shading its roots, and then it might prevent itself from growing. But as a seedling, that would not happen yet. So you understand my problem. So I have a problem imagining how self-shading would lead to a diffuse tree line. But maybe I don't know. Can the participants talk?
Yes. So I was going to say, Walter, if you'd like to raise your hand, or I can go ahead and unmute you, Walter Oberhuber. And then while we're organizing that, there was another question in the Q&A from Maria as well. But first, let's see if Walter, are you able to respond? To unmute here. Okay, Walter, it looks like we should be able to hear you now.
Can you hear me?
Yes.
Yes. Okay. Yeah, that's my problem. Even a seedling experience a low temperature if it develops close to the forest line, or it's always below the shade. And therefore a seedling will develop, in my opinion, maybe several meters above the closed forest line, because then it is full sun exposed, even the soil is full sun exposed, and therefore the roots will develop much better as the seedling would develop just close to the forest line. And therefore, I always explain it like this way to my students. Therefore, we have this diffuse forest tree line boundary or ecotone in the Alps. Or in the Alps, there's always a diffused tree line because it's too cold to get a sharp, abrupt tree line. The soil is too cold for root growth, and root growth, of course, has a strong influence on stem growth, on photosynthesis, and therefore the natural condition is a diffuse tree line, not because of seedling mortality, but because seedlings need an open habitat, open microsites to develop a root system which is able to supply nutrients, to develop mycorrhiza, and that's not possible if it's closed, if it's too close to the forest.
Mm-hmm.
Do you see my
yeah, I think I see your point. I still have problems to really see how that works in practice, because in most diffuse tree lines, I think there is plenty of space in between the established trees where trees could still establish, but they don't. Right, so you'd have to be quite...
Yeah, yes, I understand. Yeah, maybe because the root system is very spreading, very large, to a large area.
So then it would be... Yeah, so, but that would not affect the soil temperature. So then you would think it's more like underground competition.
Maybe this way, yeah. Maybe this is an additional effect. Yeah.
Yeah. So so fitting that. So that would be an interesting one to see to what extent underground competition plays a role. Because if you look at very dry mountains, of course, there you get, even the forest tends to be very open. And then towards a tree line, they tend to get even more open, which I guess may be underground competition for water in that case. So, but I'm not sure that has been elaborated, that idea. Like, to what extent underground competition would prevent trees from establishing?
Yeah, maybe there's a lot, at least there's a lot of competition with alpine grasses or shrubs, and of course there is competition, I'm quite sure, but I have to think about it. Your point, I understand now your point, that there's a lot of open space, and of course there should be more seedlings, but in the end, as soon as the shedding of the root system, there is a problem with root development, I think so. And then if you have no root growth below this 5 degrees centigrade, then you have no stem growth, no decrease in photosynthesis, and there's a limitation. As in my opinion, it's not only the above ground is important, the temperature, also below ground. I'm sure it has an effect.
Yeah, it must have.
Yeah.
I think, yeah. Just in the order of things, I think a tree would first have to make shade before it shades itself. So you understand what I mean?
Yes.
So for seedlings, that wouldn't apply. They would have to at least get to a certain stage and then maybe freeze and then not be able to get bigger, because then they are like, preventing their own growth. But then they would have to be there at least as small trees, I guess.
I will have to read your paper and then maybe I will come back again. Thank you.
Walter, thanks for the question and engagement. A couple other, we're almost out of time, but a couple other questions from the Q&A. Maaike, so Maria was wondering if the models you're developing could explain the difference between the actual and potential tree lines, if you have time to address that quickly. I think you're still on mute, Maaike.
Yes, sorry. Partly, yes. So I think at least in our conceptual model, it's already the case. So this null model would theoretically, if everything is in stable state, then in the null model, the tree line should go to the potential tree line, because the potential tree line is defined by the growth limitation. And then if anything comes on top of this growth limitation, then the tree line should start getting below the potential, basically. So, and that we are able to see in the model. So, it would be the tree line would get lower. Of course, what we cannot see. So, in a lot of cases, the actual and potential tree line are away from each other because of disturbances. That is not in the model yet. At some point, we would like to do to put it in a landscape, but that's a few steps further yet. Let's read. Do you include climate change in the model with simply shifting the growth limitation line, or does it mean line dynamics? That's one option. So that is one option to so the growth limitation line would basically be the growth rate. So the growth rate gradient, we could shift that. We could shift it up and then see if anything happens. And then in some situations, so of course the model needs some time to establish a forest and a tree line, and then it starts. So we would first try to establish a tree line and then change the climate and see how the tree line responds to that. Basically, yes, we would shift. So one of the things we would do is shift growth limitation. Of course, we could also shift the snow period or something in later stages where we're actually modeling more microclimatic processes. There we could also change other aspects of the climate. Yes, I don't know if that answers the question. Yeah, the integration with satellite images for the modeling. There are a lot of methodological challenges that we have encountered. The first methodological challenge in the remote sensing is that we are looking for high quality data that is available also in the less industrialized parts of the world. And that is already quite challenging. So I have a PhD student, Nishta Prakash, who is working on exactly that. She's like developing a methodology to use remote sensing images, and the methodological part, that's the next challenge. But the first challenge is to really get nice data. So we've been in touch with different data providers, and of course, the nicer images usually cost something, and then we are trying to to get some special conditions because we do academic work, etc. But that is actually quite a big challenge, because we want to develop a method that other people can also use. We don't want to develop a method that is based on expensive software and expensive images, because that's not going to be applicable for a lot of people, like for a lot of researchers in other parts of the world. And so that is our current challenge, actually, to get an overview of what is available, because what we want is basically what you can see in Bing Maps or Google Earth, that quality of aerial images. That is actually quite nice, but we don't have access to that in a form that we can actually analyze it. So you can see it as a base map, but you can't use it. And so that's what we are at the moment. So if anyone has good ideas there or how to go about this, that's
yes, perhaps we can even help with geomountains with some of the imagery and geospatial data.
Cool.
So we're slightly over time. Thank you everyone so much for joining today. Thank you, Maaike, so much for sharing your research and for responding to the engaging questions. I just wanted to quickly share that the research shared today grew partly out of an MRI synthesis workshop. And so we've shared in the chat the 2021 call for synthesis workshops in case anyone would like to apply and do something similar. We also shared the link for the next lecture in the series, which will be in June and will probably be of interest to many of you as well, looking at nature-based solutions and transformative change in social ecological systems. And I see some more comments coming in saying, thank you, Maaike, thank you so much. Yeah, we really appreciate everyone coming here today and helping us celebrate 20 years of our changing mountains and our changing alpine tree lines. So thanks again.
Yes, thank you. Thank you for inviting me. Thank you everybody for being there and for asking nice questions. And hope to see you in some other occasion, maybe in real life. That would be good for change as well. Ciao.